have a little bit to go in section 4.4, and then we're going to do 4.5. So in 4.4, we've already gone over the first fundamental theorem of calculus. There's a second one as well. And so we'll see how they're different from each other. This one basically is designed to show us how differentiation and integration are just inverses of each other. So here they're showing us this chart. If you have on the left the interval of f of x dx from a to b, this is a definite interval, as we know. This will give us a constant as our answer. The result will be capital F of x. Remember in this book, the interval is often written as capital F of x. And then what they're showing us over here is that it can be written equivalently as the interval from a to x, and then we change the variable from x to t. And so here we're treating this as a function t, and now the interval becomes a to x. Now, the reason for doing this, and they're showing to in this graph, is that if I wanted to calculate under this curve, f of x equals sine of x, the area between 0 and some random constant, in this case, that happens to be pi over 2, that they're showing us that we can do this in stages, but we can do it all at once by integrating directly from 0 to x. So in fact, although it's kind of a small gap there, you can see this is illustrating the idea that we can integrate this function from 0 to x, and we specify what x is, by the way, cosine t dt. And that gives us this area here. Okay. So, and then here they're tying all this together by showing me that if we take the derivative of an integral, it'll just bring us back to the original function. Okay, so like here, for example, if we started out with this derivative, now if you notice here, just like in the previous slide, we've got the interval of the lower limits of integration are 0 to x. So we're using t inside the actual function, but what they're showing us is that if we differentiate this with respect to x, it just brings us back to the original function in terms of x. So in other words, differentiation and integration are inverses of each other. Now we have this net change theorem, which is kind of useful for certain applications, like especially in physics. And so you see the way it's written. Remember, f of x is the integral of f of x, lowercase f of x, prime of x is the first derivative of capital F of x, which in turn is simply equal to f of x, or lowercase f of x. In other words, capital F prime of x means you've taken the integral and then you've taken the derivative, and now we're bringing back to the original value of f of x. So the net change of a function looks like this. And we'll do an example in a second. The computer is just a little slow today. Very slow today. There we go. All right. So again, this is the net change theorem. So here's the example they're going to give us. So a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute. Okay, so t is the time in minutes, and the time is restricted to being between 0 and 60. How much flows into the tank in the first 20 minutes? So What they're telling us here is that we're going to let CT be the amount of chemical in the tank at a given time. So it stands to reason that the derivative of CT is the rate at which the amount of chemical in the tank changes as time lapses. In other words, the rate of flow of this chemical into the tank over time. So that would be represented as C prime of T, although you could also write it as dC dt. And so this is the formula that determines the rate at which the chemical flows into the tank. And that's per unit of time. All right. So going back to the problem. Oh, and also we have to keep an eye on that the domain of this function is restricted to 0 to 60. So C prime of T, now the way they've written it, it may not be clear from the way it was written, but it flows into the tank at a rate of 180 plus 3T. In other words, that's C prime of T. Okay. So maybe it wasn't as clear as it could have been, but the flow, the rate of flow, that means that's our C prime of T. And they're interested in knowing how much flows in during the first 20 minutes. Okay, great. So the T is minutes. So that means that what we're looking for here is the integral from 0 to 20 of T prime of T dt. Okay. And so basically now we just solve for it. All right. So first, remember we can break this up into two parts. And then we can always factor the constants out, which we probably should do because that makes it less confusing. Okay. Now let's look at the first one. So the integral of T is simply T. And also keep in mind too, we won't need any constants in this case because this is a definite interval that we're solving for. So you'll have T. Now the T itself is being evaluated between the values of 0 and 20. So we're going to write it like this. Now over here, the integral of T using the power rule is T squared over 2. And again, we're evaluating from 0 to 20 based on the first fundamental theorem of calculus. Therefore, that gives us. So you're evaluating the function at 20, and then from that, you subtract the function at 0. So we have 20 minus 0. Here we'll have 20 squared over 2 minus 0 squared over 2. So 180 times 20 plus 3. Now we're going to have in here 400 over 2. This is just 0. So basically, what that's telling us is that after 20 minutes, okay, I don't know what happened there. Let me fix that real fast. After 20 minutes, the tank will contain 4,200 gallons. Let me just fix that. Okay, so the next example is this physics example where we're going to look at velocity as it relates to the speed of a particle. So we imagine we're looking at the paths of, let's say, electrons, and we want to know how rapidly the particle is moving, but we also need to know if the speed is changing. And so we have this relationship here between velocity and speed. And so we're going to use definite integral to figure out how far the particle has gone. All right, so this is our formula. So, and by the way, they're going to make a distinction between two different concepts. One of them is called displacement, and one of them is distance. Okay, so in other words, if you look at these graphs, you'll see this is what they're referring to as displacement and distance traveled. Displacement, as you can see with this graph, means that when we go above the horizontal axis, that counts as a positive area. When we go below, that counts as a negative area. And then when we go back above, that's a positive area. So the net, if you add all those three together, that shows you your displacement. In other words, where are you at time at point B compared to A? Okay, now here it looks like we've gone up just a little bit. So the displacement would be the difference between these 2 points. But the distance is a very different matter. The distance means how far did you travel along this path? So if you notice the two formulas look very similar to each other, the difference between the two is that the displacement, with the displacement, the where the curve is above the horizontal axis, that counts as a positive number. Below is negative. Down here, if you notice, they've written this as the absolute value of the t, which means that we're literally just adding up all three areas, and that will show us how far we had to travel to get from A to B. Okay, so let's copy this into the notes. So again, this first one is displacement. And this takes into account the actual signs. And the second one is distance traveled. And that one uses absolute values. Okay. All right, so let's look at an example here. So here's a formula for the velocity of a particle moving along the line. And you can see it's a cubic function, so it's going to move up and down along the way. So we're going to start out by calculating the displacement over the interval t equals 1 to 5. Okay, so we're only interested in that range. So keep in mind, t is bounded between t and 1 and 5. So the displacement means that we're going to use the signs, the actual signs. We're not going to use the absolute values. All right, so let's do that. So first of all, we need to know the actual integral of this function. And since there's 4 terms, that means there's going to be 4 sums that we have to combine. In other words, here, although they didn't show it to you directly, there's three parts of the curve because there are three terms. Here we're going to have four. Okay, so we're going to take this integral from 1 to 5, and we're going to actually add up whatever we get. Okay, so for this one, it's the displacement. All right, so let's integrate it. So the first thing we should probably do is break this up into four separate intervals and add them together at the end. And now we can easily see how to apply the power rule. So this first one will be t to the fourth over 4, evaluated between 1 and 5. Here we have t cubed over 3, t squared over 2, and then this one is just t. All right, so using the first fundamental theorem of calculus, we're going to do this. By the way, it might be easier if you factor out the constants from these expressions, but it's not absolutely necessary. Well, let's see how it goes. And then we got one more. I ran out of space. Okay. So in other words, in each case, you substituted 5, and then you did 1, and you subtract 1 from the other. Okay, let me just double check and make sure everything's in order. Yep, that looks good. All right, so it's going to take a while before we can combine all these into a single number. So for example, here we have 5 to the fourth, and that's 625. So 5 to the third is 125. And then finally we have minus 20 times 4. All right, so now we have to start combining some of these fractions. All right, let's see. 624 divided by 4 is 156. So this one, 29 times 24 over 2, that's actually 29 times 12. And that's 348. All right, so I guess we need to convert them all into thirds because 1240 is not evenly divisible by 3. So we'll have 468 thirds minus 1240 thirds plus 1044 thirds minus 240 thirds. All right, so we're almost there. So I have 32 thirds. All right, and again, remember what this is. This is meant to represent the displacement because we kept all the signs. Now, as far as the distance traveled goes, we're just going to use this formula. So it's the same integral, but we're going to take absolute values. All right, and that would be, yeah, right here, accepted absolute values. And instead of displacement, this is distance traveled. So we don't really have to do this all over again because, I mean, this is the final result right here. All I'm going to do is take the absolute values and let's see how that changes our results. Let's see. So there's two negatives. I'll change those to positives. And that should give us the right result. All right, here we go. 468 plus 1240 plus 1044 plus 240 is 2992 over 3, whatever that is. I don't think 3 evenly divides into that. No, that would be easy, but I mean, that would be nice, but it's not the way it worked out. All right. Ah, I see. You know what? They faked us out. You know what they wanted us to do? They wanted us to take the not to act just absolute value everything. They wanted it to be done specifically between 1 and 4 and then 4 and 5. The reason for that is because um, the velocity function over here, if we graph this, wow, this is going to be a little tricky. What they wanted us to do, so this is clearly not correct. I had a feeling this was too simple. Um, what they meant for us to do is find where this thing crosses the axis. So we would have had to set this equal to 0 and then solve for the point where they cross and then break it up into two terms based on where it crosses the axis. In other words, they didn't just want us to take the absolute value of the individual terms. So yeah, they took this and factored it out to t-1, t-4, and t-5. But remember, we're only interested in the area between 1 and 5. So the crossover is here at 4. So what they meant for us to do is take this area and then this area and then take the absolute values and add them up. And then if you do that, the result will be 71/6 feet. All right. So now we've got a couple of knowledge checks, of course. Let's just check these out. So here, there's no physics application. It's just solve for the definite integral using our normal techniques. All right, so we'll break it up into two components. All right, and then we can factor out the constants. So we'll have 2 times the integral from 0 to 5 pi of t dt, and then we'll have 5 integral cosine t dt. So for the first one, we'll use the power rule. Now for this one, if you remember, we do have a list of basic um, trig integrals here. And if you recall, the integral of the cosine of u is the sine of u. Okay, so that means here we have the sine of t. And by the way, these cancel each other out. We might as well take advantage of that. So we'll have t squared evaluated from 0 to 5 pi plus 5 sine t evaluated from 0 again to 5 pi. And of course, according to the first fundamental theorem of calculus, that means what we're doing is evaluating the function at 5 pi, and then we'll do the same thing for 0, and then we subtract. All right, so what do we have? So this is just 0. Now over here we have 5 times the sine of 5 pi. I'll get that from my calculator. What do you know? It's 0. The sine of 0 is 0. All right, so you can see everything dropped out except for this 25 pi squared. Great. So that's our answer. And that would be letter D. Beautiful. All right, so here's the knowledge check, number 2. Now this one's a little bit different. So what they're asking us to do is take the average value of the function f of x equals 48 minus 12x squared over the interval from -2 to positive. Now, how do you calculate the average value? All right, so what you're doing is this. All right, it came up earlier in the slides, but this is the formula they're looking for. 1 over b minus a times the integral from a to b of f of x. All right, so they've given us a and b right here. So we're going to have 1 over 2 minus 2 integral from -2 to 2 of 48 minus 12x squared dx. All right, so now that we've set it up correctly, the rest is pretty straightforward. We can break this up into 2 separate integrals. I've already factored out the constants, as you can see. So we'll have All right, and of course we use the power rule for both of those integrals. So here's what we'll get. Whoops, that's 3. So here we're going to have 8 thirds minus 8 thirds. One quarter. 48 times 4 is 192. This is correct. 192 minus 12. Now in here we have 16 thirds. Um, 192 thirds. So we'll combine everything into thirds. Created 4 over 12 is 32. All right. So that, in other words, the function's average value is 32. So, let's go look at Symbol Lab for a minute and take a look at this. Well, it's kind of hard to tell by looking at that. But yeah, but yes, we got it's 32. You see, it's very tall. I'm not surprised here that it's 32. And that, of course, would be A. All right. Now that was 4.4. There's only one more section in chapter 4. So we're going to go on to 4.5 right now and at least start it. This is a very complicated section, by the way. This is a completely new technique for solving integrals. It's a very powerful technique. You'll see it on a regular basis. Every time you do integration, this is always going to be potentially one of the options you should think about using because you see it in very many applications. It's called integration by substitution, or sometimes it's called U substitution, and we'll see why later. And what it does is it essentially lets us take integrals from functions that originally started out as composite functions rather. Right. So you have to visualize that you're taking a composite function and essentially reversing it back to its original form. So what exactly would do? Let's see. Here we go. Now this is going to be hard to visualize what they're telling you to do here. So once we've done a couple of examples, you'll see it's not that bad. So again, the logic here is that we're taking, remember from earlier, a composite function looks like this. Okay, so f of g of x means that it's a function of another function. And you also remember that when we took the derivative of this, this is the result. Okay, so here's the big question. How is this substitution method related to this? Because what you're doing is you're integrating a function that looks like this. F of g of x, g prime of x. Uh, it ends up being, okay, now remember the capital F is the integral. The lowercase f is the original function. So the integral itself is a composite function. Okay, so anyway, let's do some examples. I mean, it's very abstract the way it's written right now. So let's say we have this setup. So we first have to ask ourselves, is it possible that substitution would work in this one? Well, let's see if we can identify g of x, f of x, and g prime of x. Maybe it works. Okay, so if we let's just try g of x to be the x squared plus 1. And then f of x would be x squared, so that f of g of x is x squared plus 1 squared. And then g prime of x is 2x. So do we have what we're looking for? Let's find out. All right, so remember the form that we need is right here. So do we have that? Well, we just showed that f of g of x is x squared plus 1 squared. We saw that g prime of x is 2x, and dx is just dx. So what do we have? X squared plus 1 squared 2x dx. Okay, so that means we can use this method. And if we do, what will that result be? All right, right here. The integral of f as a function of g of x plus c. So what exactly does that mean? So because f of x, the original function was x squared, so therefore you're going to get f of g of x will be g of x cubed over 3. And since g of x is x squared plus 1, That's going to be your final result. Now that was a lot. Now we're going to need to practice a lot with these. But don't you worry, we will, because there's a lot going on here. But I think once you get a little practice, you'll see that it's not quite as bad as it looks. All right. Now, also, there's another way of doing this, which I think is a little simpler. And so here they want you to try some of these. So, for example, this one. So the first thing we have to do is see if we can use substitution in the first place. So let's try letting g of x be x squared plus 1. F of x would therefore be x to the fourth, so that f of g of x is x squared plus 1 to the fourth. G prime of x would be 2x. So if you plug all those in, you'll see that we have there you go. Although the order is slightly different. So that means that our result will be, so f of x is x to the fourth. So if you apply the power rule there, and you'll get x squared plus 1 the fifth over 5 plus 6. Now, they haven't really introduced it yet, but I'd like to show you how you would use the so-called use substitution approach, because I really do think it's simpler. We'll go back to the beginning. And it's up to you to decide which one to use, of course, but I do believe that it's my opinion that use substitution is a little bit simpler. And of course, it'll give us the same results. So we're going to let u be x squared plus 1. That means that du dx is 2x, which implies that du is 2x dx. And so what in the world does that do for us? Let's rewrite this as x squared plus 1 to the fourth 2x dx. So you can see what we've got here is u to the fourth du. And now we can apply the power rule. And then substitute back the x squared plus 1 for u. And you're all set. I think you'll agree that's the usual way to go. And later on, you'll see in the book, mostly this is what they're going to have you do. They just want you to know that there's two different ways of expressing this result. But you'll notice how in many books, they simply call it use substitution because most people will end up using this approach rather than what we're doing up here. Now, the next one is this right here. Again, we have to ask ourselves whether or not it's possible to use substitution. So let's think about it this way. By the way, if you guess wrong with f of x and g of x and all the rest, you could try it again. You can. It's not always super obvious which one you should use for f of x and g of x. So If you get the wrong one, you can try it a different way. So we have here, all right, great. So yes, we can use it. So anyway, so let's go ahead and try it. Um, Remember, this is going to give us the integral of f of x with g of x as its function. So now remember here, f of x is x to the 1/2 power. So you're going to have here, instead of 2/3 x to the 3/2, it'll be 2/3 g of x to the 3/2 plus c. And remember, g of x is we define g of x as x cubed plus 1. And there you go. Now, if you decide to use u substitution, what will happen differently? Well, you'll get the same answer, of course, but instead you'll do this. So, by the way, how do you find the u? Basically, look for the most complicated part of the expression, and like if you've got x cubed plus 1, whatever the exponent is, that's the exponent you're going to get when you integrate the u. So don't let u be the square root of x cubed plus 1. Just let it be x cubed plus 1. So then du dx is 3x squared, which is the same thing as saying that du equals uh, 3x squared dx. So all this becomes radical u du. Okay, even though they're a little bit out of order, it is radical u du. So look how easy this is. So you end up with 2/3 u to the 3/2 plus c. And now, of course, you have to replace the u. And of course, it's the same thing. All right, 2/3 x plus 1 to the 3/2 plus c. Now, the third one, now, of course, there's trigonometry involved. These guys love trigonometry. They can't let's get away without a single trig function here. So in this case, we have to be careful. Why don't we go back and revisit our charts or tables to remind ourselves if one of these, if the derivative of either secant squared of x equals the tangent, or maybe it's the other way around. So let's go back to our list of differentiation, the one I put on bright space, and we have this is all we needed to know. The derivative of tangent x is a secant squared of x. All right, so that tells us to let g of x be the tangent x plus 3. Then f of x would just be x, so that f of g of x is tangent 3x, x plus 3. And then um, g prime of x will be secant squared of x. So we can definitely use the method of substitution, because if you look at it, you'll have, what do we have here? We have f of g of x, g prime of x dx. So f of x, because f, the function is x, that means the integral will be x squared over 2. So that means that when we apply our substitution here, we're going to end up with g prime, let's see, g is tangent, there it is, tangent x plus 3. So we're going to have tangent x plus 3 squared over 2. All right, and now if we try u substitution, so we have here u du. It couldn't be any simpler. And it's it. That's it. We're done. So they're all going to be similar in the way that they get set up. Now, of course, we have to be careful because sometimes it'll appear at first glance that an integral can be solved this way, and then it'll turn out that that's not the case. You'll know because if you keep trying, like let's say here we couldn't get it to work, we try u letting u equal something else, and it still doesn't work. We have to ask ourselves if maybe we did something wrong, and maybe this is not the right case for substitution. All right. Um, oh, now here they're just making the case that sometimes if it looks like you could have used a substitution, but you're missing a constant, you can just go ahead and supply it yourself. We've seen this before. Like here, for example, let's use this as our case. So let's try g of x equals x squared plus 1. F of x is x squared. Um, that means that f of g of x is x squared plus 1 squared. G prime of x is 2x. See, there's the holdup. We don't have 2x, do we? That's the missing piece. So here's what we're going to do. By writing it like that, now we're in pretty good shape because you can see that we do have what we need. It's just that we now have that half out there. So this is f of g of x. This is g prime of x dx. So f, the integral here is x cubed over 3, which means that you have x squared plus 1 cubed over 3. Okay, now what about u substitution? Well, let's try u equal x squared plus 1. Yeah, we don't have a du. We have to provide that extra to ourselves. So we actually have the integral of u squared du. Oh, whoops. You know what I just realized? I missed the 1/2 here. That's better. Yeah, I left, it was sitting out there outside of the integral. I lost it. It's there now, so we're good. But it would be very easy to do that. So you have to keep an eye on that kind of thing. All right. So yes, so that means we're going to have u cubed over 6 plus c. And of course, we know that u is x squared plus 1. And it's the same thing. It has to be. All right, good. Now, up to this point, everything we did was based on indefinite integrals. Okay, so oh, actually, no, we're almost there. Here is they're formally introducing the U substitution. I've been kind of showing it to you as we go along, but here they're formally introducing it for the first time. So here's what you're doing. And you can see, by the way, this is why it's called often called U substitution. So let's try u equals 2x minus 1. By the way, if you get this wrong, you can just try again with a different value. It's okay if you miss it. You know how you'll know if you pick the wrong value of u, you'll just end up with an expression that's even messier than the one you have now. So in other words, you're not helping yourself is what's happening. So that would imply that what we have here, so we're missing the 2. Let's remedy that. And now what we actually have here is, okay, and now of course we can use the power rule, but first let's rewrite this as u to the 1/2. I just think it makes it a little easier to do it that way. So we end up with 1/3 u to the 3 halves. And remember, u, we chose it to be 2x minus 1. And there it is. Beautiful. Okay. Now, here they're trying to give you some helpful advice because, like I said, it's not always immediately obvious when you look at an integral. First of all, if you should be using substitution, and secondly, what should you use to represent u if you're using u substitution. But again, usually the way it works out is if you've gotten it backwards somehow or incorrect, you'll notice it right away because the result will be even messier than what you started out with. Now, here is an interesting result. These are both equivalent to each other, depending on whether you're using the f prime of x, g prime of x notation, or the u notation. But they both mean the same thing. This is called the general power rule. And it works like this. Now, keep in mind that u is a function of x. So if you have x, this is the regular power rule. This is now known as the general power rule. And so you can see what's happening here is u is not just x, it's a function of x. It could be literally any function of x. So, I mean, it looks like the same thing, but it's important to recognize that u is not just x itself, but it's a function of x. So, now, by the way, we've already taken advantage of this a few times in some of these examples. So, ooh, here's a nice messy one. Um, oh, no, here's some more. Oh my God, look at all of these. Well, of course, we need practice. All right, well, let's start with the first one. So let's try u equals ux 3x minus 1 du dx is 3, which we do have. And so we end up here with integral of u to the 4th du. And that means we have and there we go. 3x to the minus 1 to the 5th over 5 plus c. Beautiful. Now for this one, we have, ooh, now you might look at it and panic a bit. No, there's no need for that, but it may not be clear whether you should use or let u be x squared plus x or 2x plus 1, or if maybe neither one of them is correct. And then you should try a different technique. So let's see what we can do. Now, by the way, sometimes there are workarounds too. You could, for example, simply multiply all those terms out and then integrate them individually with the power rule. But it might be quicker to do it this way. So I'll tell you what, now usually the rule of thumb is that the u should be the most complicated function. So let's try u equals x squared plus x. What do you know? If you rewrite this slightly, oh, that was very easy. This is u and this is du. Well, it doesn't get any simpler than that, but of course that's because we picked the right choice for u. If not, we would have an S on our hands. Okay. And now this last one, and once again, why don't we try u equal x cubed minus 2. So we'll rewrite this slightly. And that's going to leave us with, and of course we can rewrite that as u to the 1/2, which is what it is. And then we, of course, substitute back for u, which was x cubed minus 2. Okay, and that's our final result. So these, if you look at these integrals carefully, you'll see they look pretty terrifying. Um, but luckily, this technique is really good at handling these very messy polynomial integrals. It doesn't always work, of course, but it can help in a lot of cases. Oh my God, there were more. Okay, let's try these. And of course, like I said, they can't get away, let's get away without at least one trig problem. All right, how about this one? So let's try 1 minus 2x squared for u. So here's our du. So all we have here is, yeah. So we can think of this as, and of course, u is 1 minus 2x squared. Or of course, they rewrote it as minus 1 over 1 minus 2x squared. because of course it's the same thing. All right, and then of course now here we are. Now to do these, you do have to know the trig derivatives very well, or else of course look them up in our table. We have the integral of cosine squared x sine x. Now, because the cosine is squared, let's try u equals cosine x. So based on the table, the derivative of the cosine of x is the negative sign, and we don't have that. So we'll need to provide it. And so what we now have is this is du, and then this is u squared. And that's it, we're done. By the way, I want to mention something here about exponents and trig functions. Most textbooks will write positive exponents for trig functions like this. Just so you're aware that these are the same thing. When it comes to fractional exponents, they don't do that. But for the positive integers, this is the normal way it's done. All right. So what else do they have for us? Oh, all right. So this is what I started to say earlier. Every one of these cases that we've seen so far was a definite, an indefinite integral, meaning we were not looking for a specific value. We were looking for a function plus a constant. Okay, so all of those cases that we just saw were indefinite intervals. But if we want a definite integral, we do have to do one important thing differently. And that is that the limits of integration must be redefined in terms of u. Okay. In other words, you can't leave the limits of integration are not going to apply if you switch from, let's say, x to u or something like that. So, you know what, I'll tell you what, it looks like we've been running for a long time here. So we'll save this for next time. This is the last part of 4.5. So we're this close to being done with chapter 4. So the next time we meet, we'll wrap up this discussion. It's not that complicated, but we'll save that for next time. And then we'll start chapter 5. Now, 5 is different because we're going to suddenly stop spending so much time with polynomials and trig functions and spend a lot more time with logarithmic and exponential functions. So well, that'll make things very interesting. So anyway, so we'll cut it off right here and we'll save this discussion for next time. So I'll see you then.